So I mentioned it in the last video about how you could explode the structure into various two-force members and apply basic Newton's laws onto the free body diagram. So that's what this is called. This is called the method of joints. There's actually different ways to solve truss problems, but this method is called the method of joints. And it's very robust, very time consuming and tedious, but it does allow you to analyze every member in this structure. So I'm going to draw the free body diagram of this. So we'll start with the point C, for example. So if we look at the point C, we're going to have something that looks like this. I'm going to choose a different color. So we have a C, the point or the joint C. We're going to do something like that. And the force interacting on this point is this two-force member BD. So I'm going to say it's in, I don't know, in tension. So I'll draw the force pointing in that direction. So that'll be FCB. And then for the other two-force member, which is right here, that is, I'm going to say it's also in tension. So I'm going to say it goes that way. So FC, or the CD. And then now that we have those forces right there, here, let me redraw the labeling so it's different from the forces. So I'm going to say this is going to be C. Oh, hold up. So this is going to be C. And then now we look at the members themselves. So we drew the reaction forces of the member BC and CD. So we could draw those. So what I'm going to do, I'm going to draw something like this. And then you get a reaction force by Newton's third law. You draw it in that direction, and that'll be FCB, the reaction force. And since this is a two-force member, then the force acting on this end must be pointing in the opposite direction, but equal in magnitude. So that'll be FCB. And then here, let's draw the CD member. So that'll be here. So then the reaction force by Newton's third law will be in this direction. So it'll be FCD. And then also using Newton's third law, this should be FCD. And now we're going to draw the joints at B and D. So it'll be something like this. So B, this will be B, and this will be D. So let me label those real quick. So the reaction force should be pointing in this direction, FCB. And then if we look at the diagram, there's a two-force member going in that direction, horizontally across, and this angle, which we don't know. And then there's another force by this two-force member. So we could draw that. So there's a force going in that direction, there's a force going in that direction, and there's a force going downward. So that's how this joint would look like if you explode it from the other components of the truss. So there's just reaction forces acting upon this diagram or this joint. And what we're going to do is repeat the process for D. So there's only a reaction force going in that direction and in that direction. So what this would look like, you would have a reaction force going that way, which is FCD. There'll be a reaction force going this way, and then there'll be a reaction force going in this direction. And then we could actually draw this bar right in the middle. So something that looks like this. I think I drew it too wide. Something that looks like this. So we could say this is that reaction force and that reaction force right there. So that's going to be FBD. That's going to be FBD. And this is going to be FBD. And then this reaction force on this two-force member will be FDE. So I think you guys get the point, and you basically repeat this process until you have the whole free body diagram that consists of each different member, including the joints or the connections at which these two force members connect with each other. So I'll leave it up to you to do the rest. I'm not going to do it because this is actually very tedious, and this can show why this method of joints is very tedious and time consuming. but it does allow you to analyze every member or every joint in this truss, which can be useful for the just basic analysis of structures. Maybe some members are in tension or in compression, and you need to know when these two force members will buckle and stuff like that. So this can be helpful, but it's also very robust and time consuming.